Okay, close those up for a second. I'm going to take just a little time out here. I'm not opposed to giving you some time to work on this stuff, because I know people, you know, there's been a lot of stuff going on surrounding Roundup, before Roundup, and I'm okay with letting people kind of catch up a little bit with this stuff. But what I want to do now, I want to do something really cool. Let's go back to the discussion we talked about yesterday, because this is one of those things in physics that you're going to think is pretty interesting. There's a lot of hidden gems here that sometimes people just overlook what the physics gods are really trying to tell us when we ask them a question like this. So we started this one at the end of class yesterday. Just real quick, suppose a car merges into freeway traffic on a 200-meter long ramp. If its initial velocity when we start the stopwatch, we start the camera, is 10 meters per second, and it accelerates at a rate of 2 meters per second squared, how long does it take to travel the 200 meters up the ramp? Okay, got a picture of that, right? Mental picture of that. This kind of summarizes things a little bit. Our initial position is 0, right? So that's our displacement we're measuring, right? It might be good to just remind ourselves of that. So this distance up here is really just displacement. The initial velocity is 10, final velocity, we don't know. Our displacement is going to end up being 200 meters, and they tell us what our acceleration is, right? And so we looked at that and we said, all right, so what's going to be the formula that matches all of that stuff? If the things that we're trying to find are, or the things that we're given are displacement, right? We have a number, initial velocity, right? Acceleration. Right? And what are we trying to find? Time. So if we think about that list we had yesterday of all the steps, that's a lot of steps. Summarize the information. We found out the things that we were given. We found out the thing we're trying to find. And then we're looking for an equation. Yes, sir?
The Vmax should be 10.
Oh, 10. Sorry, it's not 0, is it? Yep, thank you. There we go. And you told me correctly that the equation we want to use is the third one, right? The one that involves displacement, initial velocity, acceleration, and time. But it's different than what we've dealt with in the past, because this time, whereas all the other, and there have been a ton of examples, but all the other examples we previously looked at had allowed us to just isolate a variable and then plug and chug, right? This is different. The variable shows up twice, t and t squared, and so we recognize that when we can't really isolate t this time, right? We've just got to plug in the values and write this as a quadratic equation in standard form, right? We want to set it, we want a to be positive. A quick review, if we go back to Algebra 2 stuff, right, we know that quadratic equation in standard form is just that, right, with x's instead of t's. We want to set it equal to 0, we'd like a to be positive. So if it's negative, we just multiply by -1 and flip all the signs. Check. That meets our criteria, doesn't it? A is 1, B is 10, C is -200. So we're able to factor this pretty easily, right? We can find magic numbers that multiply to -200 and add to 10, +20 and -10, right? And then what do we do once we factored a quadratic equation? We apply the zero product property, right? Set the factors equal to 0. Remember why that is, right? We know that, don't lose sight of what the zero product property does, right? Zero product property just says that if you multiply, if I had you, do this in your head real quick. What's 10 times 5, okay, just in your head, keep going, divided by 2, okay, times 13.3, okay, hurry up, times the quantity pi minus 1, okay, times 1,109,047.32. No, that's a lot. So times 0 equals 0. If we multiply by 0, we get 0, right? So the only way we can get a product equal to 0 is if one of the factors is 0, right? So remember, what the zero product property is really saying here then is the only way we can accomplish this is if this factor is 0 or that factor is 0, and those represent the mathematical solutions, right? I'm sure that you knew that, but let's just put it in the right terms. So one solution then, the first factor is 0 when t is negative 20, the second factor is 0 when t equals positive 10. Okay, how do we interpret those results? What do you think? Richard, what do you think about those results? Which one are we probably looking for? Positive 10, right? Because we're imagining that when we do this, we're thinking in terms of a video camera, right? We start the video camera at t0 when our velocity is 10, that's our acceleration, and right? And we're going to, does that make sense? We stop the video camera when we've gone through displacement of 200 meters. And if we look on that frame of the video camera, there's going to be a little 10 seconds, 10.0 seconds, right? Okay, so we asked the physics gods when this stuff happens, and they gave us 2 answers. Were they pulling our leg and joking with us here when they told us that the negative 20, is that worth anything?
It's the time it would take if the acceleration was negative and the distance backwards.
Okay, so almost. You want to restate that because you're really close to how we interpret this. What does first of all, what does a negative 20 seconds mean?
Traveling backwards in time.
Okay, so you're traveling backwards in time. That sounds fairly glamorous and weird, but all that means is, if I snap my fingers now, and then I snap my fingers 5 seconds later, and let's say that's what we're going to call time 0. When was the first snap? Negative 5 seconds, right? It was 5 seconds before the second snap, right? So negative 20 just means 20 seconds before we started the video camera, okay? That's not a crazy answer. Let's think about why that is. What are some ways we could represent this motion? I want you guys to kind of lead this as much as you can here. How could we represent, we've talked about some graphical ways of doing it, right? So what if we were to use like a velocity time graph, for example? The initial velocity is 10 and the acceleration is 2, right? So if we use a velocity time graph on this, and the reason I do this is most of the time, we would just say, like you look in the textbook, it's just going to say, okay, disregard the negative 20, that doesn't make any sense. It does. In its own way, it does. If I've got a velocity time graph, what does that look like if my initial velocity is 10 and my acceleration is 2? Okay, so the line's going to be 2x plus 10, isn't it? My initial velocity is the start value. Let's just go by tens, right? And the acceleration we said was 2, right? So our line is going to go through that point. It's going to go through that point, and it's going to rise and run by, that's 10. It's going to look like that, isn't it? Right? Okay, so what does the area under a velocity time graph represent? Do you remember?
Total distance.
Displacement, right? So we wanted to know when our displacement was 500, right? Does that make sense? Wasn't that what the question asked when we'd gone 500 meters? Oh, 200, is that what it was? Okay, so we want to know where is that going to be? At what point is the area under this curve going to be 200, right? Because that's going to tell us, that's one way we could have solved for t, right? Does that make sense? So if we just call this, let's just call this t. Interesting way to do it, isn't it? How would I add up this area? Okay, I've got a triangle, and maybe I've got a rectangle, right? So what if we broke it into 2 pieces? What are the dimensions of that rectangle then? 10 by t. We don't know how wide it is yet, right? I mean, we solved it. We now know that, what was the answer? I forgot already. 10? Okay. So it's going to be, the area of that is going to be 10, a height of 10 times t, right? What about the triangle up here? What's that going to be?
1/2 2 times. whatever a panel was.
Yeah, how are we gonna do that? What's the height of this thing gonna be? What's that gonna be? What function is this? What line is this? You told me it's the line
2x plus 10.
y equals 2t, I guess, right? 2t plus 10, right? So the height of this thing is going to be, well, there's my 10, right? So just this part is just 2t. So isn't it going to be 2t times t, right? But I want 1/2 of that, don't I? See where I'm going with this? So the area of this guy, that area, here's the yellow area. The blue area is 1/2 the height. What's the height? 2t plus 10, but I'm already starting at 10, so that's going to be 2t times the width of t, right? So it's just t squared. See what I'm saying? Does this equation look familiar? Does the equation t squared plus 10t equals 200 look familiar? Bet it does. Oh, what do you know? T squared plus 10t equals 200, so if we subtract the 200 of that, does that make sense? You see we get the same equation? How about that, right? So we can get there using the graph too, right? Okay, but what's going to happen if I work backwards on this graph? Because we're making the assumption that we start the camera there and we stop the camera there, right? But the physics gods aren't making that assumption when we asked them this question. We didn't say anything about starting and stopping the camera. We just said at this one moment of time that we're going to call 0, these are the conditions, right? When we stopped the camera, we calculated what the time was. But the assumption is that this is just a piece of a continuous motion, right? So the motion ought to continue backwards before when we started the camera and on after we stopped the camera, right? So what does that mean I could do with this graph? If I go, right, I could just do this, couldn't I? I could just go back. It's just going to continue on back like that, isn't it? Right? So when is the displacement, at what point is the displacement going to equal a total of, now it could be negative, but at what point is the displacement going to equal negative 200? When do you think that's going to happen?
Negative 20.
Negative 20, right? If I were to pursue if I were to go backwards, right, at some point back here at negative 20, I'm going to look at the area under this curve and what's going to happen, right? The area under the curve here, I'm going to get a little bit of positive and a little bit of negative, and if I add it all up, I'm going to get a value of negative 200. Everybody agree? We could do the math, but you see how we're going to get this answer? So the physics gods were pretty smart about this. They wanted to know when we had displaced ourselves a distance of 200 meters. Well, previous to this, that's when it would have happened, 20 seconds earlier. If you think about it in terms of the motion, just kind of play this movie in your mind here. If I'm going to be the car, all right, I'm moving in the positive direction and I'm moving at 10 meters per second and I'm accelerating at a rate of 2 meters per second squared. In what direction is the invisible hand pushing me? That way, right? So I'm getting sped up like this. Let's run it backwards. I'm going really fast. I'm slowing down. I'm slowing down. I'm slowing down. Eventually, that hand's doing what to me? So stopping me, and I'm going back in this direction. See what I'm saying? You get the idea? So if you work backwards through this problem before time 0, yeah, the car just oscillates back up the ramp, right? I mean, if you go backwards in time, the physics gods are assuming that this car was zooming backwards in reverse, invisible hands pushing it forward and slowing it down. It's coming to rest. Now I'm picking up speed. There's where we start the camera. I'm going 10 in that direction, but it's pushing me faster. Now I've gone, see what I'm saying? Physics gods are wise in the ways of science. They know what they're doing, right? They gave us a reasonable answer, just it wasn't the question we were interested in answering, right?
Or if you have to deal with that? Like, use it?
Yeah, you could. What if, okay, I'll give you an example. Why would this be important? Well, what if I were to rewrite this problem in a different way? What if instead of a car merging onto a freeway, accelerating up a ramp, let's say that we've got a charged particle that's in an electric field, right? And it's oscillating in an electric field. It's going back and forth then, isn't it, right? Does that make sense? And so then we would have just been starting the camera when it happened to be here, but it's actually doing this, right? See what I'm saying? And so then that would be a pertinent answer. Or if it were, maybe it's a mass on a spring that's oscillating sideways on a spring, on a frictionless surface, or up and down, right? Does that make sense? So yeah, it could. That could be important in some situations. Okay, last thing I want to say, I'll let you work some more. I'm not going to add much to this at all. We have our list of, you have your list of equations, right? Okay, just get that out real quick. So, I'm really anxious to talk about gravity with you, because gravity is really interesting. I'm not going to do it today. I want to let you work, and we'll come back to that. Friday would be a great day to talk about gravity. We've got our equations, right? Delta x equals v bar t. What do we got? Delta, we have v equals v naught plus at. We have delta x equals v naught times t plus 1/2 a t squared, right? And then the last one we have is v squared minus v naught squared equals 2a delta x, right? Does that make sense? Okay, what if, let's take an object like, I don't know, like this pencil. If I'm holding it in my hand, what is its acceleration? It's 0. Einstein might disagree, and there's a different perspective we could take where we wouldn't say that. It's actually the best perspective, but it's not normal. We would say it's not moving relative to the floor. And so its acceleration is 0. What is it now when I drop it? 9.8. 9.8. In which direction? Down. So we'd say relative to our conventions, it's negative 9.8 meters per second squared. Okay. Let's ignore air resistance. I have, before this demonstration, I have carefully sprayed the pencil with Sliprium, which is very expensive. You get it at the Acme store. It allows it to slip through the air with no resistance. Okay, so there's no friction going on. Okay, what is it now? What if I let go of this thing and I want it right now? What was the acceleration at that point? 0. At the top. At the top. Okay, at the top. What is it right there? Raise your hand if you say 0. You said 0.
Yeah.
You think I'm tricking you, don't you?
Yeah.
You're right. It's not 0. What is the acceleration? Think invisible hand. What's the invisible hand doing to this thing the whole time it's out of my hand? It's pushing it down. The invisible hand guides us to understand the direction of the acceleration, right? So where's the invisible hand pushing on this? Right there.
Down. Down.
Down. Down. Right? So what's the acceleration, do you suppose, then? Negative 9.8. Why is it negative 9.8 if it's at rest there, right? At that one moment in time. Well, that moment where the velocity is 0, and is it ever 0? I mean, you could argue, yeah, between positive and negative values of velocity, it's 0. How long does that moment last? Infinitesimally small, right? But we get the idea. There's one moment in time where it's hovering motionless, right? 0 is nothing special. 0 is just the number in between the set of positive and negative numbers, right? What's the invisible hand doing to this thing as it accelerates? When I drop it from rest, it's easy to consider, right? After 1 second, what's its velocity? 9.8, right? Because that's what acceleration does. It tells us the rate at which velocity is changing. Gravity's pushing it down with an acceleration of 9.8 meters per second, meters per second squared, right? So it's picking up 9.8 meters per second towards the center of the Earth every second, right? After 2 seconds, how fast it goes?
Twice that.
What's that?
Twice 9.8.
Twice, so 19.6, about 20, roughly. Let's just, for the sake of argument, let's round gravity off to -10 to make things easier, right? So if I throw this thing up in the air, let's say I throw it up in the air with an initial velocity of 10 meters per second. That's how fast it leaves my hand. After 1 second, how fast is it going? 0. How come?
Acceleration and velocity.
Oh, okay, because picking up speed in the negative direction, as we said earlier, is the very same thing as losing speed in the positive direction, right? It's changing its velocity by a net amount of -10 meters per second every second. So if I throw it up at 15 meters per second, it leaves my hand. After 1 second, it's going about 5, right? About +5. Make sense? So what if we do this then? Let's say we throw it at 10 again. After 1 second, it's going 0, right? Where is it after 2 seconds? How fast is it going? -10. After 3 seconds? -20. So the whole process was just, I was changing my velocity at a constant rate, right? That one moment at the top, which we call the apex of the trajectory, it's just one instant in the infinite string of instants that occur as this thing slows down and speeds up, right? The acceleration is constant the whole time. If the acceleration were 0 there, what would it do? Slow motion camera, it would slow down and hover. That would be weird. That's not normal, right? That would be strange. But it doesn't do that because the acceleration is -9.8. So it continues to change its motion downward, right? Okay? All right, so then if we're going to consider the case of free fall, free fall is it just means the only force acting on an object is gravity, right? So if we ignore air resistance, if we're going to spend less money on this stuff, and we load up a cannonball or a football or anything, and we launch a projectile in the air, which we'll deal with later, that's complicated. It's two-dimensional motion, right? But once the cannonball leaves the cannon, or the football leaves the quarterback's hand, ignoring air resistance, how many forces are acting on it?
2.
What would the forces be?
Gravity and initial.
Okay, but once it leaves my hand,
It's just gravity.
just gravity, right? That's free fall, right? The only force acting is gravity, so it's in free fall. Now, we're not going to deal with that complicated situation yet. For now, our free fall is going to be vertical. Either I'm dropping something, or I'm throwing it downward, or I'm tossing it upward, right? So we're not going to worry about the horizontal component of this stuff. We'll deal with that later. But once it leaves my hand, if I'm throwing it up or throwing it down, it's in free fall. Only one force is acting on it. It's gravity. The acceleration of gravity is a pseudo-constant, right? It's relatively constant near the surface of the Earth, right? And so what can I do to all these equations to make them pertain to that one instance where we're talking about free fall? How would I change all these? There's one little thing I could do.
Change acceleration to 9.8.
Okay, yeah, the acceleration is gravity, isn't it, right? So we would say A is equal to T, or negative G, right? Does that make sense? What does little g stand for?
9.8 meters per second.
Yeah, it just stands for the rough acceleration of gravity near the Earth's surface. Is it truly constant? No, it's not. Why wouldn't it be constant?
Different distances from the center.
Okay, for one thing, different distances from the center of the Earth. If you drive up to the top of Cabbage Hill, you're a little further from the center of the Earth than you were at the beginning. Now, you have more mass underneath you, and so it's not that big a difference, but it is slightly different. Even on a flat surface, why might it be different?
Sea elevation changes are very subtle.
Okay, but what if the elevation is absolutely flat, let's say? Gravity's going to change very slightly. Why might that be? Okay, I'll give you a hint. Geologists use a microaccelerometer to determine what type of sedimentary rock is under their feet. Density of the rock, right? If you're standing over basalt, that's dense. Standing over basalt, the gravity is going to be, like in Pendleton, is going to be slightly higher than it would be if you were on the coast and it was something light like sandstone, right? Okay, so you can use a microaccelerometer to measure these very tiny changes in gravity. You get a pretty accurate map of what's beneath your feet, right? But we're going to ignore that. Those are minor, minor changes. And so for all intents and purposes here, this is about negative 9.8 meters per second squared. And if we make that one substitution here, if we just call acceleration, you know, I don't like using the negative sign for g. I'm going to go ahead and do this. Let's write this as g, and we'll just know that g is negative. Does that make sense? Because then all we have to do is, right, g is negative. All we have to do is just change those a's to g's, and we're set, right? We can. So let's say, for example, how much time we got?
4 minutes.
4 minutes? Oh, okay. So here's the example I wanted to consider. Is what would happen, this is what we will consider. This is the next thing we're going to do. I'll put an assignment up, but this is the next problem I want to do that's pretty interesting. Let's say, for example, that we are standing, here's the ground, here is a tall building. What's the tall, somebody Google real quick, what's the tallest building in the world? What is it? Okay, how tall is it? Find out. Quick, find out. In the world.
2,717 meters.
Wow, 2,000, that is high.
That's
Feet.
It's
Feet, okay, that's still high.
829.8 meters.
What is it again?
829.8 meters.
Okay, 829.8 meters. So the height of our building is 829.8.
Yes, it is.
Okay, we are going to fire a bullet coated with slippery straight up in the air with a muzzle velocity of 1,000 meters per second. That's pretty fast. That's about, what is that? 3,300, something like that, feet per second-ish. So pretty fast, right? But that's doable, right? I'm not a hunter, but some of you guys probably, high-power rifle would do that, right? So we're going to shoot that bullet up in the air. We want to predict when it's going to hit the ground. Okay? We're going to do several things. Let's predict how high it goes. Let's predict when it hits the ground. Let's predict how fast it's going to go when it hits the ground. Then we can do all that stuff with everything we now know if we just consider that the acceleration is g, right? Okay, so that's what we got in store for tomorrow. We'll take a look at that. Okay.